All right, welcome everybody, both here physically and online. So I'm Peter Rayner, and I'm lucky enough to be introducing Kevin Gurney today. I think I can say that Kevin's career has been on a continuous downward trajectory. Started work in stratospheric ozone, and then spent quite a few years working in the troposphere, so the lower part of the atmosphere, thinking about greenhouse gases, trying to map and estimate their sources and sinks and understand the uncertainties about that. And that's where Kevin and I worked closely together, particularly around a fairly high profile paper on producing a global map for these things and understanding its uncertainty. And then I think Kevin was one of the first to realize that one of the things that underpins our use of these methods was an assumption about what the fossil fuel sources and sinks were, which turns out we don't know so well. So there was a science driver for trying to map these better, but of course there's also a whole range of policy drivers. And so Kevin has, on a few other people, really led the charge over the last few years into much more rigorously based and high resolution mapping of particularly the anthropogenic sources of fossil fuel down to really small scales, understanding not just how you can do this, but what you can do with it as a policy instrument, and trying to think about mitigation of the climate below national scales. I also should say that along the way, Kevin spent quite a bit of time kind of closely involved in the policy process around some of the negotiations, and I suspect, like a few people, he could swap some interesting and probably legally actionable war stories about life inside the negotiations. That might be a question for another day. So Kevin, it's yours.
Thank you. Thank you, yes. And thank you very much, Peter, for that excellent introduction. It's almost more articulate than what I'm going to spend the next 45 minutes saying. But, and thanks to Malta for inviting me out here to the college. It's really a lovely spot and a great collective. I came here a few weeks ago for Miles Allen's talk, which I thought was excellent. So clearly, I'm holding up the back end of talks like that, but I'll do my best. So I'm going to talk about what has been, I guess, an evolution of kind of moving from CO2 inventories to what I'm hoping is going to become a very more sophisticated information systems on CO2 fluxes. See if I can get that pointer. Yes, got it. Whoop, whoop, come back. No, it's okay. There we go. First, a little bit about where I'm coming from in the world. This is, I'm coming from Northern Arizona University, which is in a little town called Flagstaff, which is in the southwest. You always know it's because it's got this tiny little bump showing up on the map, which will become clear in a minute. Now, most people think, when they think of Arizona, they think of this, right? Big, giant, funny looking plants that assault you if you get too close to them, right? Full of prickers. Or the places like the Grand Canyon. And that makes up actually only about half the state. The other half of the state, which has very few people in it, are places like this. Pretty mountainous, lots of snow. In fact, Flagstaff is the only ski resort in the state of Arizona, which again, most people would never expect. But a beautiful spot up on the Colorado Plateau. I also want to put up quickly one slide on Senator Fulbright. I am here on a Fulbright Scholarship for 4 months. This is a program that the US does with many, many countries around the world. Some of you may know it. It began sort of during the Second World War by Senator Fulbright. And the idea was to increase scientific, cultural exchange through these sort of programs of sending people back and forth. It's had almost 400,000 students, academics, professionals in the program, and very strong program with Australia. Over 5,000 scholarships have been awarded. I bring this up not just to pay dues to the Fulbright program, but because between last year and this year, the program has doubled in size, and next year the Australia-US program is going to double again. So if any of you are ever thinking about doing a Fulbright scholarship, I would say now is the perfect time to do it before everybody else catches on to how big the program is becoming. Right, the political winds change the program. Although it seems to have weathered politics pretty well, because it's attempted to sort of be a fundamentally apolitical program, even though its roots were, of course, not. Okay, so a quick outline on what I'm going to talk about. I'm going to try to go through a bit of history, the last maybe 15 years, to try to identify what I think are a series of forces that have been pushing mainly the scientific community, but I would say scientists and a lot of practitioners in this world of characterizing greenhouse gas fluxes towards this information system, which I'm going to try to describe. I'll go over three nested scales, three different scales of this information as we have it now. We're going to see if there's some requirements that have been set out and whether or not we're meeting them or not meeting them. And then I'm going to talk a little bit about some of the work I came here to do, which is trying to do some of this work for or on the city of Melbourne, depending on how you think about it. So first, when most people think of a greenhouse gas information in general, they'll think of an inventory. And the classic traditional instrument for that is the nation-state style inventory. This was born out of the international negotiations. And it's kind of nation-state defined. Usually you generate lots of tabular information about what are your fluxes, break them down by sector, maybe do that over multiple years. But it fundamentally was a sort of counting up of emissions. For the obvious reason, if you're going to do anything about reducing greenhouse gases, CO2 in this particular case in the atmosphere, you got to know how much is going in, where it's coming from, who's responsible, so on and so forth. But I would argue there have been, since that initial kind of template that began really, it goes back to about the 1980s when this sort of notion of how people were going to do this counting up. Since that time, there have been a variety of forces that are starting to push this in a new direction. One of them is, I think, embodied by this report, which is from the National Research Council in the United States, that really was a document communicating to the scientific community the fact that there's an emerging need within the policy world around verification, monitoring, reporting, and verification. Now, this came out in 2010, which is a bit late, frankly, but it was really the result of 10 years of discussion, I think, and even pressure, a lot of that coming from the policy sphere. That's kind of a icon of the 1997 Kyoto Protocol negotiations, about 2000, Copenhagen, and so on. The evolution of the international negotiations were clearly bringing up the fact that there needed to be some system for monitoring, reporting, and verification, although admittedly, within the policy dialogue, it's a very sensitive topic for probably obvious reasons that whenever anybody hears verification, they think about who's going to do that, who's going to be telling nation states how to do it, what to count, whether they violated things or not. Within the scientific community, I would argue verification is a much kind of softer notion, and that we tend to think of it as we really want fluxes to be correct with what we measure in the atmosphere. Those two need to be internally consistent, not as politically loaded as the way that is discussed within sort of policy or political circles, and both understandably so, right? The other thing that started to come about was our ability to observe CO2 around the planet began to change drastically. This is what I think of as the traditional or ground-based observing system around the planet for CO2. This is the system, or a subset of this, is what gave us the sort of iconographic maps of CO2 and the rise of CO2 from the South Pole, et cetera. But as you can see, it's plenty of holes and gaps in this observing system down at the surface. If you look at fossil fuel CO2 in the atmosphere, of course, this is what it looks like, which dominated by Northern Hemisphere emissions, pushed around by weather, right? So this just looks like almost anything you would emit into the atmosphere that doesn't have a lot of chemistry, but just gets pushed around by the winds. The difficulty with that map is when you compare it to that observing system I just showed you, it's clear that it's very difficult to capture all of the detail in that map, both in space and in time. And that's really what pushed, again, starting in the 1990s, but finally realized in the late 2000s, was new platforms to observe CO2 from space. We're still in the midst of learning how to use a lot of that data, but the promise is that you'd be able to look down on the planet, combined with that very powerful ground-based observing system, and begin to really map CO2 in a much more fully comprehensive way and be able to illuminate or at least disentangle all those tendrils and tails that you see when you look at CO2 as it moves around the atmosphere. There's 2 instruments flying right now, a Japanese satellite, a US satellite. Another one's about to go up, although the launch just got moved. Yeah, I don't know when the...
Should have been this morning.
Should have been this morning, and now it's in 1 month, 2 months?
No, it's a couple of days.
Oh, only that, okay. So very soon, we'll have the successor to this instrument flying, and then many more planned after that. In fact, it's become a pretty busy bit of science. Another force that evolved over the last 10 to 15 years is the fact that a lot of the policy requirements are starting to go down in scale. And I would argue it sort of really came to head in the late 2000s. I've put up California's climate change bill here because it's our shining example in the US, but all we have. But it just shows that the entities that were being involved in climate mitigation in a very formal policy political way were going below the nation state. Now, you all know there's plenty of cities that have gotten involved in this. The C40 network. Cities have become very important actors, both at the international scale and then individually in their own right, sometimes as part of networks, sometimes by themselves. And it's always important to recognize that fossil fuel CO2 emissions on the planet are, of course, not evenly distributed at all. They're very concentrated, no surprise, in cities, which we think account for now roughly 70%, almost 3/4 of energy-related carbon emissions on the planet, even though they're a teeny bit of the surface area, which of course makes a remote sensing strategy pretty challenging, right? You have this tiny bit of the landscape, which is accounting for a huge amount of what you're trying to measure. The area of cities is supposed to triple by 2030, and urbanization occurring rapidly, doubling by 2050. And all those trends are now pretty well established. As you all know, we're moving into a planet that is fundamentally urbanized, and hence the role of cities within the larger climate mitigation policy discussion has become crucial. Another force that I would argue that has pushed us all in a particular direction is the recognition that though when we started out, the view of the system was a system of nation states that emit within their geopolitical boundaries, and we just need to figure out how much those emissions are, to the fact that the world is fundamentally tied together in ways that make assigning responsibility pretty tricky. And it really is the distinction simply between supply and demand, that you can define the world as a production perspective, that is, where is CO2 leaving the surface of the planet, moving through the atmosphere, where is fuel being burned in the case of fossil fuel CO2, or you could think about it as where are all the demand for the things that drive energy consumption. Now, some of that is coincident in space and time, but a lot of that is not, because of the complicated supply chains we have all around the planet. This is an example of some work that was done between nation states, but we're trying to even do this now between states in the US and even between cities. And it adds a very complicated dimension to the construction of information systems around fluxes. And I would say the final one that I'm going to touch on here is, as Peter mentioned when he was introducing me, is the fact that we've kind of realized that our understanding of these fluxes that we thought we knew pretty well is fairly poor when you look below the nation state level. Mainly because, you know, we mostly relied on statistics of sales of fuel around the planet, but within countries was never a particular interest. And now that it is, it's clear that we don't have a lot of information about how both fuels and the demand for products and all the other things that fundamentally drive emissions happen below the nation state scale. This is a map from sort of the mid-1990s, and if I were to blow this up, sorry about the US bias, for just the United States, this is what that map used to look like. And it was really just coal, oil, natural gas being sold between the US and other countries, distributed on the landscape by population. The perfectly reasonable spatial proxy, but if you really want to get down to brass tacks of where emissions are occurring, probably not a very good one. So that's sort of the final element that was starting to make it clear to the scientific community and a lot of the practitioner community we were working with that we needed to really revisit flux quantification and do a completely new and in some ways very different job of constructing the information. So all of these forces, I would argue, make for a series of requirements that we probably need to meet. First, we want to have granularity, right? We want to have some detail in space and time that is down at some scale that's useful. And we'll get around to how much might be enough. Clearly, this has to be linked to the atmosphere. I didn't come out and say it straight away, most of you know it, but of all the bits of the carbon cycle that we can observe, measuring the atmosphere is probably the best and most robust bit that we know. We can measure it extremely, extremely well. It integrates all the emissions, so it has the virtue of sort of not missing anything, if you will. You can conserve mass in the atmosphere. So linking to the atmosphere in some way is very, very important because it offers, again, that sort of anchor to a very well-established and very accurate assessment of an amount. We need process information. So not just numbers in squares or numbers coming out of an entity, but why? What's the process going on? Does it have to do with combustion for energy? Does it have to do with making a product? Is it driving a car? More process or deterministic information about what's going on. Because when we start to use that information in policy, having a lot of that detail can become really critical. And finally, it needs to be linked to some transparent, traceable, independent scientific standard that has some consistent methodology. Okay? So those are what I would argue are sort of the key requirements that we want to have in building a new system. So now what I'm going to do is maybe run through some work that I've been involved with in attempting to try to satisfy some of those requirements. Obviously not the only one that's doing this, but I'm going to show some examples. The first one is an effort to create fossil fuel CO2 emissions at the global scale. This is work that was actually started by Peter that I've worked with him on now for a few years. It's called the Fossil Fuel Data Assimilation System. It's not the only data product out there that does this for the globe, although I think it's unique, but there are really only 2 or 3 that are really worth their salt, in my opinion. We're sort of starting to bear down on about a 1 kilometer spatial scale over multiple years and trying to do this hourly. Now, this system is primarily built from satellite information. Not entirely, but mostly. And this work is ongoing. Lots of new iterations of this, but this is sort of one point in this tour of these different scales that I want to show you. The next one is, and again, I'm using US as the example here, is an attempt to take a very different approach to creating this information. Rather than sort of using satellite remote sensing looking down on the planet, we're going to try to mine information across the landscape from various data sets and put together what's typically referred to as a bottom-up inventory or assessment of fluxes. This is a project called Vulcan, which began in probably the late 90s, early 2000s. We put out our first version of this in 2007 or 8 or so. It was made for the year 2002 for the United States, and it attempted to quantify fossil fuel CO2 in 10 kilometer square boxes every hour for a whole year. And in addition to the granular detail, it had a lot of process information. So we had information about exactly what device was doing the combustion, whether it was a vehicle, what type of vehicle, what type of road it was on, if it's a boiler or a turbine or whatever. Lots and lots of information, all of it fundamentally mined from publicly available federal data sets. And in the US, like Australia and a lot of other high-income countries, we collect lots and lots of data, sometimes through census, sometimes because of energy markets, so on and so forth. And really all we did was go out and just collect it all and bring it into a singular system. There wasn't any new data that was brought to this problem. It all pre-existed. It just hadn't been collected, gathered, and worked through to create this type of information. Now, since that time, we've continually tried to improve it. We're now doing this at about, I would say, with reliability at around a half a kilometer. For the whole US, we now do multiple years, again, every hour. And as I said at the outset of the talk, there are various ways you can think about the fundamental accounting that you're, or accounting perspective, I would say, that you're trying to solve. The idea of emissions coming out of a physical domain, leaving the surface and going into the atmosphere, is typically referred to as scope 1 accounting systems. Okay, people are probably familiar with the scope idea. Vulcan fundamentally is a scope 1 data product. And the reason it is because it was driven initially by linking to the atmosphere. The idea was to create boundary conditions to these atmospheric models that would solve aspects of the carbon cycle. And so we needed emissions that really did talk to the atmosphere in a very direct way. In other words, it's not attempting to do the supply chain problem between consumption and production. Although we're beginning to move in that direction. We've now created what's referred to as scope 2, which means we take all the emissions from all the power plant facilities in the United States and we allocate them back to where the electricity consumption is occurring. And we're doing this down to pretty fine scale using a transmission and electricity balance model in the US. We're even now trying to do scope 3. So we're actually trying to push all the way out to doing supply chain CO2 down at this scale. Now, that's a hard thing to do, extremely uncertain, but we're going to try to do it nonetheless. We've also then gone down probably in the late 2000s, early 2010 or so, we began to try to push even further and try to go down right into an individual urban landscape. Now, we've only done this for 4 cities in the US. We're working on a 5th. And the idea here is to go right down to every single building envelope, every single road segment, airport, facilities, industrial facilities, et cetera. The whole kit and caboodle. This, by the way, is our on-road CO2 segment, just showing the major roads. The green was the residential building sector, and the red is the commercial building sector. This is like the Vulcan project. This one's called Hestia. Vulcan is the Roman god of fire. Hestia is the Greek goddess of the hearth fire. I'm terrible with acronyms, so I have to revert to mythology. It's very similar in that it's mining a lot of local data. So it's just in taking Vulcan as a starting point and then seeing if there's additional data that a city might have that might inform a more detailed approach to the inventory. This is all 3 sectors together. And indeed, in this time evolution, you can't quite see it here, but you actually see the residential sector wake up. You see it start to decline as the roads pick up. That declines at the end of the rush hour and the commercial sector picks up. You see the evolution of people as they move through their working environment, expressed through their CO2 emissions. And as I say, we've done this in the US for 4 urban domains. The first one we did was the city of Indianapolis in the Midwest United States. That particular domain is a bit unusual because we've also merged it with very intensive measurement of CO2 in the atmosphere. Remember, these flux data products are just the estimate of the fluxes coming out of the surface. But in Indianapolis, we've instrumented 11 cell towers with very, very good CO2 monitoring instruments. They actually measure other things as well, CO and methane as well. Flying aircraft over the city with a downward-looking flux measurement system. And then also mounting devices in cars and driving them around the city as well. This has now been done in lots of cities, not just in the US, but elsewhere. But we've also then, the second big domain was the Los Angeles domain. It's actually about 80 cities. We've just finished Salt Lake City in the upper right, Baltimore in the lower left, done with lots and lots of investigators from universities and institutions. There's a effort I'm not so involved with it, but an excellent effort ongoing in Boston. And then we're beginning to move outside the United States to do this in other places. Paris has had a long-standing experiment, much like this, that has sort of almost been functioning in parallel with the work we've been doing in the US. And then, as I'll talk at the end, trying to do a little bit of this here in the city of Melbourne, and an effort that's just begun by colleagues in New Zealand, in Auckland, New Zealand. So starting to spread, and this sort of very urban intensive type of approach to quantifying emissions is starting to pop up at various places around the planet. So ultimately, we would love to nest the three different kind of scales that I've talked about. That was not necessarily the intention at the outset. But now that we're tackling this problem at these three scales, it of course makes sense to conserve mass. One of the great benefits of doing this between the globe and down to the building. I can't say we've done that yet. We've actually nested these two bits, at least in the US, quite well. Our urban results and methodology really nests fully inside the nation state. And they're, from a mass point of view, they're internally consistent. We haven't quite done that up to the global scale, although if you give Peter a couple of weeks, he'll probably do it. But we're working across that, working on it anyway. One of the benefits of doing, I'm going to talk alternatively about the Vulcan system, which is a national type of high resolution system, and Hestia, which is that super duper detailed urban system. I'll talk alternatively about some of the benefits you can get out of doing this problem both ways, and hopefully meet some of the requirements that I set out at the outset. So just Vulcan, just doing the entire landscape at about 1 kilometer allows, in many ways, an instant inventory for any city in the United States. And this is just an example of a few of these cities just carving out the Vulcan result. This is Chicago, San Francisco Bay Area. I can't even tell what that's. Houston, right? Houston and Beaumont in Texas, Boston in the Northeast, New York, Philadelphia, Washington, DC, etc. So you can imagine, straight out of the box, one of the virtues of doing this consistently, methodologically across the landscape, is you have an instant scope 1 inventory for every single city in the United States. Important because right now, as you know, it's occurring here in Australia, it's occurring in a lot of countries, cities are actively trying to generate inventories. There's nothing wrong with that. I think it's a wonderful thing to do. But in some ways, I would argue, it's not the most efficient way to go about this problem. You probably can do it all at once in one fell swoop, instead of what is becoming this kind of almost plodding cottage industry of everybody creating their own inventories. It has lots of political buy-in value, and I don't want to dismiss that. I think that's actually very important. But from a technical point of view, it's probably not the most efficient way to do it. When you do all the cities in a country, you can start to also see lots of dynamics across the urban landscape all at once. For example, in the US, this is amazing to me. The top 5 cities in the United States are like the 8th largest country in the world in terms of emissions, right? They're right behind Iran, ahead of South Korea. Now, again, just speaks to the drastic log normal nature of fossil fuel emissions in the world. Top 50 cities are number 3, just in the US. Not in the world, just in the US.
Where would Australia be on that?
Say it again.
Where would Australia be? How far out would you go?
It's not far off. Somebody will have to tell me, but I think Australia is certainly in the top 20.
16, I think.
16, thank you. Makes sense, yeah. This is a comparison of these Vulcan urban results of scope 1 CO2 emissions relative to what I'll call the self-reported inventories that cities are doing, okay? Tempted to carve out the exact same city outline, tried to use the exact same scopes, gathered all of these city inventories and just simply looked at them in comparison to the information system we're developing in the US. And by the way, this is not to suggest that either one of these is correct. I actually honestly don't know whether Vulcan is right or whether Vulcan is wrong. We like to think it's right. We have some atmospheric linkage that seems to confirm it's pretty good, but it could be wrong. Really, the main point I want to make here is that there's still drastic differences between the type of assessments we're making in cities and what cities are finding in their own efforts. Again, that's not to suggest they're wrong, but it's just to point out that we're not anywhere near where we need to be if we want to support cities with these type of information systems and find kind of a singular approach, maybe, or the best approach to quantify emissions at the urban scale. We can do lots of interesting things. I'm going to show you one example of this. We could ask a question like, well, if the US is not going to, as a nation state, try to meet its Paris commitment, which right now at least we've indicated that we are not, how many cities in the US would require it, and by how much reduction would they need in order to get the US to comply unintentionally, right? And so we can ask that. Right now we have sort of, on paper, a 27% reduction below 2005 levels by 2025. It's about 450 megatons of carbon. From 2015 forward, it's about 250 megatons of carbon we would have to reduce to get the US to comply with Paris, even though politically we've said we're not going to do it. We can ask, well, how many cities and at what additional effort would be needed to fill this gap for the entire country as a whole? And we did it a few different ways. It depends on what you define as a city, because again, a city and its urban boundary is different depending upon what discipline you're coming from. Economists think of cities one way, urban geographers one way, social science another way. There's no singular definition. So we did a few. But I think probably the most, one of the most common ways is through this urbanized area. And what you find that if you get the top 250 cities in the US from 2015, if they made less than a 30% reduction, the entire US would be de facto in compliance with Paris. Now, this is now quite dated. You know, we have something like 400 or 500 cities that have pledged to meet Paris. That doesn't mean they've done it, but they've certainly pledged. So this is well within the realm of possibility. And again, just emphasizes the power that cities have. They have a lot of executive authority, at least in the United States, and certainly have the numerical potential to actually do this. Okay, it's well within the realm of possibility. But again, having all the cities quantified centrally and singularly allows you to really start to look at questions like this. I'll show a couple slides about the power of granularity, because when we first started this work, there are many people that said, this seems like overkill. Why do you need to go down to every single building? I mean, this seems ridiculous, right? And there are lots of interesting reasons, lots of things one learns, not just from a scientific point of view, but there's lots of policy potential that you derive by understanding your landscape in this kind of detail. This is Salt Lake City. This is just the residential building emissions, some examples of clusters of buildings that we've quantified in this system. These are just the broad emissions. These are the emissions per capita in all those buildings. And though it may be a little blurry from where you're sitting, there's a very, very strong east-west gradient in these emissions. They're very dominated by the portion of the city that's actually up against very tall mountains right next to here. However, if you look at that same emissions distribution, but look at it per unit area, the pattern shifts dramatically. It's actually much more of a north-south type of dynamic, right? This is emissions intensity, at least per unit intensity versus per capita. Now, depending upon your policy goals, and I would argue in most cities, at least right now in the US, there are very few cities, even the ones that have pledged dramatic cuts, that are going to tackle CO2 emissions by themselves as a singular policy goal. Often it's in conjunction with other things that they're trying to achieve. For example, in Salt Lake City, there's a lot of interest in improving building envelope, but doing it primarily in low-income parts of the city. There was interest in improving the on-road transportation system, but in high congestion zones or areas that were flow through from home to work. So again, lots of co-benefits that are all very much associated with the type of urban planning that those of you that do that know all about. It is very, very specific. It's very particular. You need to know your landscape in very detailed ways to be able to really efficiently engage in a lot of those policies. And so CO2 often these days is sort of coming along for the ride in a lot of these systems. And so we have to quantify it in the same way, at the same level of granular detail, and with that same kind of functional, mechanistic information content. Here's just another example from Los Angeles. This is the LA domain, that's the residential sector, I think that's the commercial sector. This is just simple cumulative emissions of on-road CO2 in LA, broken out by 100-meter squares. And perhaps not surprisingly, the cumulative emissions always look like this, right? That a very small percentage of the physical landscape accounts for a vast majority of the emissions. In this case, 10% of these 100-meter grid cells account for 60% of the emissions. So again, if your goal was to do something with your on-road sector to mitigate CO2, there's no sense doing that everywhere. You go to the few places where you get the biggest return on investment, and you need to know where those are and why they are. So this is all very nice, the pretty pictures, there's lots of detail, but how good is it? Is this really any good, or is this a lot of pretty pictures? And at least in Indianapolis, we've spent an awful lot of time, mainly because, as I said, it's a place where we've been measuring the atmosphere with a lot of instrumentation of various types for a fairly long period of time. And this is just to show the Hestia flux emissions here, atmospheric transport in the middle, a very detailed atmospheric transport model, and then the CO2 monitoring down here. This is actually one of the tall towers, and indeed, that is the aircraft we fly around the city. We in the royal we, I don't fly an aircraft. And the system is to essentially run this backwards, right? Is to go from the receptor point to the emissions, and in many ways really iterate between the two to see how well we can get consistency between these fluxes that we build at the bottom and the atmosphere that we observe. And indeed, ultimately adjust fluxes so that they best match the atmosphere, so that we both gain the strong anchor in atmospheric measurements, but create a detailed landscape that's most useful to carbon mitigation. So we've done, in the city of Indianapolis, done a fair amount of work trying to see how well these two approaches to quantifying the landscape do, and it is surprisingly good. Now, I think in some ways we're probably lucky. Indianapolis is not a particularly difficult city because of its ensemble of sources, but we get within 1 to 3% of what the atmosphere says over this domain. Now, there are a couple tricks we had to play. First of all, what we create from the flux point of view from the city landscape is not exactly the same that we measure in the atmosphere. There's biology, for example. There's respiration. We actually had to include human and animal respiration to get a little more convergence. But even in the dead of winter, incredible, but even in the dead of winter, when we ran these inversions, there's still a little biotic respiration. The soils are still respiring a little bit. So we had to include that. But even without those, we were almost within 10%. And then by topping up the bottle with a few of these other things that we know we're measuring in the atmosphere, but not quantifying in the fluxes, we get almost near convergence between the two. Now, as I said, it's one city. I suspect that the work in Los Angeles is not going to look as pretty, and we'll have lots and lots of differences, and we'll have to work on those. But city by city, we're going to hopefully build a system that is smart enough to really generate consistency between the two. Now, while I'm here in Melbourne, the goal was to try to start to put together the ingredients of a Hestia-style emissions data product in the city of Melbourne. So we've been collecting lots of data, and of course the good news is there's lots of things to start with here, right? We didn't try to do this initially in Lagos or something, which would be hard, right? The city has lots of information. There's been an inventory I think is pretty darn good, as city inventories go. So we have lots of things to start with. There's a fairly rich array of traffic style data. This is annual average daily traffic, which we rely on to a great extent, zoomed into the city. This is traffic monitoring hourly, even 15-minute traffic monitoring in the city. So there's actually a fair amount of data that we typically have relied on in those US examples here in Melbourne that we're going to put together to try to create a high resolution inventory. There's pretty good building consumption, energy consumption data here at the property scale in Melbourne. And so through data sets like this, we're starting to see a path towards creating that type of building by building estimate here. Now I say estimate, right? Because this is clearly a combination of data and algorithms and gap filling and all sorts of things one does to try to get an estimate. But, and then nest that within the Victoria and the National Greenhouse Gas Inventory that, of course, has been done for quite some time. And it's looking like we probably may not achieve it in the time that I'm visiting here, but hopefully it builds the seed to get this finished over the next few months to build an inventory for the city.
The darkest red spot on that map is University of Melbourne.
Yeah, that's right here, right? I don't know what that is. What's that? That's a park, the red part here? Okay. It'd be weird if it's a park. Yeah. But again, these are sort of the ingredients, if you will, of building an inventory. So maybe last slide. I don't know what my time is like because I see a clock, but hopefully I'm not over time. So showed the forces that seem to be pushing us towards a new way of doing these inventories. And I've shown some pieces that through a lot of science drivers and policy pressure as well, but really a combination of both, we've started to kind of build a system that's beginning to look a lot like that. It's not quite there yet, but it's starting to look that way. And of course, it's useful to ask how well are we doing so far? I mean, there's no question that we can get granularity. We can start to get a granularity, both through observing the atmosphere in much more granular detail, in mining the type of data that a lot of places around the world have, to create pretty granular approaches to fluxes. We can do it in a fashion that's consistent with the atmosphere, okay? In principle, we haven't done it a lot, but in principle, we've established absolutely that can be done. Plenty of work and plenty of extension of that needs to happen, but I think we have a good path to do that. Pretty good at achieving process-based type information, just because typically, again, mostly in high-income countries, but we have an awful lot of information that gives us kind of process detail associated with emissions. Things that need work, as I say, we're limited still to obviously very high-income places where there's transparency, both of governance and data, a lot of public sharing of data, places like that. That's a fairly limited place on the planet. Although again, if you're looking in CO2 space, it tends to be the part that matters, with the exceptions of some of the rapidly developing economies, for sure. But outside of that, you're capturing a lot of the CO2 by looking at high-income part of the world. That part about linking the supply chain, I think, still needs an awful lot of work. It's a hard thing to do, and it sort of digs into a whole different world of data that has really lived within the world of economics and in the United States, interstate commerce, and a lot of different data styles that are admittedly difficult to disentangle and use for this problem. But we have lots of excellent work at the global scale and some work in multiple subnational domains. Europe's doing a lot of work on this, the US as well. So hope here, but that's tough. I think we've got to fight to get that. So I think all in all, we've come a long way. We're close to building what I would consider to be a pretty elaborate information system that I think can serve everything from a city to nation state and solve lots of scientific problems, but we have a little bit of work we need to do. And so with that, I'll thank you all for your patience. Thank funders and the many clever people that have done most of the real work that I've shown you today. So thanks a lot.
Thank you so much, Kevin. That was excellent. Really, really fascinating research. Thank you for presenting today. I'll open the floor to questions.
Yeah, thanks, Kevin. That's an incredible project. I'm curious to know, I think you showed a figure that sort of showed the difference between self-reporting and
Sure.
And you made the comment you weren't sure which was right. I was wondering if you, I think they were cities. I can't remember. But did you, I guess, talk with any of the cities, or did you get any feedback from? Did people get offended or upset?
Right.
Or,
So,
what was the sort of result of that?
Yeah. I mean, the short answer is no. We haven't talked to any. This is actually not published yet. And in some ways, that's why I've blocked out the names, because people tend to get a little too fixated on the names of the cities. And, we need to do a lot more work before we do publish this. But one thing I will say about this, because it brings up, there's a bunch of points inside of what I think is an important question, which is how do we talk to cities about this? And I've had, at least now the benefit of having spent a lot of time talking to cities, not necessarily on here's you and here's us. It's more about, hey, here's what we're doing. How can we work with you to get this done? And by the way, to do these urban scale inventories, there's no question, you have to do it with the city. I mean, there are people within the city that you have to call on the phone to get data and to get understanding. And so there's no way one can come down from 40,000 feet and just create those type of detailed inventories for the city. But there is an important discussion that has to be sensitive to a lot of different things. First of all, what you kind of raised, which is I'm right and you're wrong, right? We've intentionally avoided that type of conversation. A, because technically we don't really know. And secondarily, that is no way to start a conversation. It will only go, sorry?
Yes, it is.
It is? In my experience, it tends to go downhill pretty quick. And in many ways, gets in the way of us achieving what we really want, which is to make a system that benefits everybody, that is as accurate as we can make it, and is free and open to anybody who wants it. That's ultimately what we want. And it can't be done, again, in isolation from cities. They have to be partners in this work. But we haven't gotten to the sort of crunch point yet on this type of thing, but we probably will within the next 12 months. There was one in the back.
One in the back and then one here. Would you mind just introducing yourself? Sorry, I forgot to mention that. Thank you.
I'm Ian Jones from Castlemaine. You said that we can't just come down from 40,000 feet or whatever and tell somebody we think is an emitter what they're doing. You also said that the satellite instrument is being deployed now. There's another one updating that. What's the chance, or what are the developments happening in observation of the atmosphere, which I think you said, and I certainly agree, is the really best way to get a notion of where is this stuff coming from. How are the instruments going, and where's the path, and where are we going to get to, and is that going to supersede some of this uncertainty?
I guess I would say in some ways we're still trying to figure out what is the right mix of what type of measurements combined with flux, bottom-up flux estimates is the kind of right mixture. I would say so far we've approached this as we often do in science, where we spend a fair amount of money to in some ways do the problem in the best way we can. I would argue there's no way we're going to reproduce the type of observational system we've put together in Indianapolis in every city of the planet. That is utterly unrealistic. It was expensive, took a lot of effort and time. I think what we're trying to figure out, combined with satellites, is what is the right mixture of observing that gets you how much improvement in your information content, right? The sort of dollar per uncertainty reduction. I don't think we know it yet. Some of that is because we still have some science to do. We don't have enough examples. Also, it's because cities, though there's a lot of common features, they are also very idiosyncratic. And so until we have a pretty big sample, it's going to be hard to conclusively answer that question. So I'd say we're not quite there yet. It's clearly going to be a mixture of, probably a multi-tiered system. Satellites will clearly have a role in this, not just, by the way, for CO2, but also just for divining infrastructure at the surface, just being able to recognize physical infrastructure. There's portions of the world, as I said, where you have very little to start with. And in those places, there's no question that remote sensing, not of the CO2 monitoring type, but just a visible, infrared, just understanding infrastructure is going to be important. But I'd say we're not quite there yet, knowing exactly what that perfect mix is of different observational bits are to get what information level out of a city.
Michael Steindl, volunteer radio presenter for the Beyond Zero Emissions Climate Solutions show. I was very interested in your discussion of US accidentally, or I think you used unintentionally, meeting the Paris targets, and the relevance of the 350 plus cities that have signed up to the targets. My question is whether the new movement that started here in Darebin and is spreading rapidly worldwide of declaring climate emergency, including in cities like Los Angeles, is going to help much with that discussion with the cities and the political momentum that will give them.
Short answer is yes. I think, short answer is yes. There's no question that, at least in the US domain that I'm more familiar with, city political leaders need to feel constituent pressure. I mean, they've taken a lot of pledges, I think, primarily because, let's be honest, a lot of that's marketing, okay? Cities are in, fierce competition with one another to attract businesses and do all those other things. So often a lot of the pledges are an outcome of that type of marketing pressure. I think to translate that into real actionable work, I think is going to take constituent pressure. So I think it's an absolutely crucial piece of the puzzle. I mean, that's almost obvious to say, but it's worth repeating that I just don't think so far at that scale we're going to move cities unless there's some real pressure from the bottom up. And it's the right type of pressure, because the one thing that I found when I've gone around to the cities in the US with this type of presentation is they're certainly interested in the numbers, and that's all lovely, but it's the communication power. It's the ability for their constituents to see their city with CO2 in exactly the way we've all become used to seeing our city, which is that you pull out your phone and you can see every street and every building, where you're going, etc. We almost now expect that. That's how we have to see every single thing in the world. And so the ability to bring CO2 into that palette is a powerful communication tool to get city leaders to motivate constituents, because they see their school, the road they're driving on every morning to bring the kids to, et cetera. And it's a powerful piece of communication.
Hi, back here. I'm Stephen. I'm a PhD student at the college. And just a pivot on that point around cities and marketing, but also linking it in with some of the things you've discussed around focusing on emissions on the supply side or the demand side, so production or consumption-based accounting. I know there's a number of cities that have undertaken consumption-based inventories. And the difference between the sort of successes that cities, including Portland, Copenhagen, others on the production side, where, they're seeing reductions in emissions and quite low sort of per capita emissions in some levels, sits like really in tension with what they're seeing on the consumption-based side. So Copenhagen, for example, is amongst the lowest per capita emissions in the world, but a report that looks at environmental footprinting broadly places Denmark amongst the fourth sort of highest country in the world. And I mean, that doesn't do much for marketing of the cities, but it also points to a really important point about action at the city level, that the emissions that are sort of put out at the source are only part of the story, and that a lot of emissions are embodied in supply chains or other goods. So I'm really interested to learn a little more about how you're pushing your work in that direction. As difficult as it sounds, on the sort of scientific side and mining data, but also the kinds of conversations that you might have been having with cities to that effect.
Yeah, so on the technical part, we are, at least, and again, in the US, there's a fair amount of data on the movement, production, sale of supply chains in a lot of, fairly detailed categories in the US economy. And we're relying to a great extent on that information. Trying to merge it with the scope 1 is kind of awkward because they're two really different ways of looking at the system. But as I say, technically it's mostly coming from kind of economic supply production statistics and a fair amount of census data as well, since some of it lives in there. And yeah, we're trying to really go from, the big difficulty in that is not so much what's moving around the United States. That is difficulty. The challenge there is just getting down in scale, really. The other difficulty is integrating the rest of the world in with that internal numerical scheme. So a lot of kind of technical hurdles, but I would say we have the benefit of a reasonable data environment to do it. But we're still working on it. The truth is this is a work in progress. It's actually while I'm mentioning it's part of a what's called a FUSE project, Food, Energy, Water Systems Project, a big push by the National Science Foundation to get people to do research on a more systems view of food, energy, and water. And so we have a project, and through that kind of energy piece, we're trying to bring in this kind of scope 3 granular effort, trying to do water and food all at that granular scale along with carbon, which is a challenging thing to do. On the discussion with cities, I haven't had deep discussions about that with cities other than the fact that you're right, some are more interested in a consumptive viewpoint, others not so much, precisely because it's a pretty daunting, not just technically, it's just numerically, it looks pretty daunting, right? Again, because of the marketing pressure. Ultimately we've got to do both, or we have to have an information system that certainly adheres to both, can talk about both, ultimately be able to view in both, partly to make this point of how fundamentally important consumptive supply chains are. That because we're fundamentally exporting emissions, not just from a nation state point of view, but even cities are becoming CO2 emitting exporters by becoming fundamentally suburban, moving industry to other less desirable places. And so we've got to start making that linkage, because ultimately, again, the atmosphere is the ultimate recipient of all this, and both ends of the problem have to be understood. That's not much help, but that's about as far as I can go. There haven't been a lot of conversations on that, at least not with me.
2 more questions. So Peter and then Malta.
Kind of a prompt for discussion point, really, Kevin. Maybe just a couple of examples or 2 minutes on thoughts about the way cities are taking up this kind of inventory information. It's a discussion we've obviously had ourselves a bit, but I'm interested to socialize with this group. What kinds of subproducts or elements of these systems the cities are finding most useful?
I'll kick it off with one comment, and I would be interested in what others think of that. But there's no question that it is through the conversation that combines air quality and greenhouse gases has become fundamental. I talked about co-benefits. The system needs to be kind of adherent to the fact that cities and provinces and states have a wide variety of things they're trying to do, above and beyond just meeting the basic services that they're sort of on the hook to do. And I think one of the sweetest spots is between air quality and greenhouse gas emissions. The United States, and I don't know about here, but we've had completely separate regulatory systems for these two things. Partly that's due to history. Air quality emerged in the 1960s as a regulatory system in the US, and greenhouse gases only recently, but they remain utterly and completely legally separate, which I think is really unfortunate, because the obvious intersection here is air quality. In fact, a lot of the machinery I've described, look, we just borrowed from a lot of what air quality's been doing for a long time. They had to confront this problem, different details and different end goal, but a lot of the machinery is the same. And I think that's an important point of intersection, particularly in low and middle income countries, where air quality tends to be a primary and acute problem that matters to high income countries, but a little less so, because we've been beating on the air quality problem for so long. But that's an obvious point that we've got to sort of discuss as we talk to cities to try to bring them along on the value of a system like this.
Thank you. Great talk, Malte from the college. In what is today and in 5 years or in 10 years, the ground resolution with which you can determine fossil fuel emissions fluxes by plus minus 10%, assuming a purely satellite-based observation and then inversion methods, etc. So no ground data whatsoever. Maybe assuming that not too many OCO satellites measure deep ocean concentrations.
Independent of a kind of prior flux guess, purely from remote sensing?
So on the global scale, purely satellite-based.
I mean, I'm tempted to pass this one to Peter because he's probably thought about it longer than I have. But I'd have to say, from remote sensing, I mean, I'd probably say we'd probably want to bring together a few species that we're remotely measuring now. So CO, NO2, CO2. With some triangulation, I think you can, in 5 years, we'll be able to look at the planet, let's say at 10-kilometer box. I'm going to say plus or minus 25%. I don't know, that might be a little optimistic, but I think we're getting there. And I think that it's the next 5 years when it's really gonna, a lot of advancement's really gonna occur, because we're just at the cusp of doing this in a much improved fashion. I might be a little optimistic. I don't know, like I said, Peter might have
Peter,
a more informed opinion.
Don't know about that. Peter,
Okay.
interjecting. The one thing to note is that you can probably do this. I might even be more optimistic about the precision, a little less optimistic about the resolution perhaps, but you will have the problem that those satellites don't necessarily label your CO2 molecules for you. So unfortunately, there's a few places in the world where there's just fossil fuel, and there's a few places in the world, there's lots of places in the world where there's just biosphere. We're interested in lots of places that have both, and we're going to have to think still about other information to help us separate those two things if all we see is what we can see from space.
Yeah, and that's an excellent point, and that is partly why I say it probably needs to be triangulated with other species simultaneously to help us get away from exactly the problem Pierre identifies.
Thank you very much, Kevin. That's wonderful. For those who have any final questions, maybe you wouldn't mind hanging around for 5 minutes at the end.
Happy to.
And as you can see, I'm madly trying to get to the end of the slides. I'm actually hoping that we can get to the final slide. We snuck one in just in the end.
Sorry, yeah, these are extra.
Yeah, no, that's fine. Right at the end, I'm hoping, it's not important. I'm just hoping we could get to the slide that tells us about upcoming seminars here at the college.
Oh yes, of course.
There it is.
Very important.
Oh, I missed it. Sorry. After all that.
That's okay. That's good. There you are.
So just to let you know, we have Ross Garneau coming up this evening here at the college, 6:30 p.m. That event currently is sold out, but you can access it via webinar, and there are registration links on our website. Monday night, we have Donna Luckman speaking on raising new home energy standards. That's a BZE seminar that will be held at the Fritz Lowe Theatre at the McCoy Building. Again, look at our website for further information. And then next Wednesday, 8th of May, we again have Ross Garneau giving his 5th lecture in his 6-lecture series here at the college at 6:30 p.m. Without further ado, could I please ask you to join me in thanking Kevin once more for his fascinating seminar today.